Hi there, and welcome back to part 2 of the Microdrone. In this part we're going to talk about the circuit diagram and the code. Link down below you'll find a link to my GitHub. On there you'll find the UF2 code. You can just squirt straight into a Raspberry Pi Pico and have this thing up and running, and also the circuit diagram. If you want to do that and go away and build it, you can. If you want to carry on listening to this video, I'll talk around the circuit diagram a bit more, and also talk a bit about the code and how it works and some of the interesting things that it does. Here's the standard Raspberry Pi Pico layout with the GPIO pins around here. Let's start at the top. So the first thing the Microdrone needs is power. I usually keep any USB cable that's gone dud, chop the end off, and then you've got wires that you can solder directly on to provide the power. So you can plug any old USB power into pins 40 and 38, plus or minus. Then we've got the two pots. One is for the frequency spread, and one is for the frequency. I used some 10k pots, but 100 would do, or whatever you've got lying about really, because it's only a voltage divider for the analog to digital converter. So pin 36 is the positive 3.3 volts out. That goes to one side of the pot. The other side of the pot goes down to ground. Any old ground pin will do. Two join together and go to ground. So as you turn the pot, it'll go from 3 volts to 0. Here's the wiper, and the wiper of the pot goes into the analog to digital converter port 1 and port 0. That gives you your two pots, gives you the variable frequency. And then the trigger switch, it just picks up another plus volt, and it provides a plus volts to IO16. So that's the trigger. So those are the controls, the switch and two pots, and how to wire them up. Then on the other side, slightly more complicated, we've got the output. These resistors really come in pairs. They're all 1k, but if you haven't got 1k, then 600 ohms or 2k or 10k would even do, I think. The key thing, because these two oscillators, these two are the ones, each pair are the ones that go out of phase. So these two need to be fairly well matched. If they're not well matched, then you'll have a rippling sound. So make sure that these, if you've got a whole load of 1Ks, make sure these two are the same, these two are the same, these two are the same. And as long as they're all around 1K, that's fine. But the pairs have got to match. If you want to do something a bit funky, you could make this oscillator, you can make these 2K, and what you'll find is that this would then have less influence on the output voltage. This is the mix switch. It's a latching switch. When you make this connection, the envelope, this button will work. When this is open, when you press this button, you're just going to hear a phase shift on your stereo output. There's two capacitors here. These I chose 0.1 microfarads. They're only really just to decouple any DC between you and wherever this goes next. Plus is this side, if they're electrolytic, and that goes off to a jack socket. So all the red oscillators mix together and go out on one channel, and all the yellow ones mix together and go out on the other channel. And then your jack socket goes in there. And that's it. It's a handful of components, and you're good to go. I do need to mention that whatever you plug into this jack socket, there's no volume control. So you're relying on the volume control of wherever this goes next. But it seems to work with, you could plug headphones in there, or I just plug it straight into my speakers, PC speakers, and the volume's about the right level. If you get a minute, do take a look at the link down below to the Microdrone. This is the grandfather of drones with 1,000 oscillators, and it's built by Look Mum No Computer, and in some ways it was a bit of an inspiration for this project, because this project has got frequency, sort of spread oscillators, and an envelope, and that's exactly what the Microdrone has, but on a much bigger scale. Let's take a quick peek at the code. The Raspberry Pi Pico has got two cores, so you can run two threads in parallel. You can do two things at once. The code I've written is all written in C, in the C language, which is very low level, which is ideal for microcontrollers because it's very efficient. The clock speed on the Pico is about 125 megahertz, 100 times slower than a normal PC. At the top of the file there's just the normal includes and definitions of the pins. There's two arrays here, ticks on and ticks off, and the phase. These are like global variables. They're appropriate to both threads of the program. Ticks on is how long you stay on, and ticks off how long you go until you go off. It sets the size of the square wave. I never change those, so my square wave is always square. But you could have like more on than off, change the width. The lamps thread, okay, well, this was a light bulb bit of code before, but now it's called lamps. This is actually the oscillators. One half of the CPU is doing the oscillators, the other half is handling all the switches and knobs and that stuff. In order to keep the correct frequency, we've got to lock this thing into time step. So I have a little loop at the top here, which causes the CPU to wait, and it waits for a specific number of CPU cycles. And once it's moved on to the correct time, the code can execute. So if the clock speed changes or there's any variations in the code, this means my square waves won't vary in frequency. So here are the 16 oscillators, and this is the code. There's a variable called tick. There's a variable called ton and a variable called toff. Tick is a number that counts up, and when tick reaches the end, or the tick off time, it resets itself back to 0. That's how the square wave is essentially calculated. The tick ticks up here, ticks up here, and when it reaches the maximum speed, the tick off time, it goes back to 0. We're doing this over an array though. We're doing this for 16 oscillators, but we're actually doing it for 8 because this here increments 16 plus or minus 2. One part covers one oscillator and the other covers the oscillator that's out of phase. So here the value of the tick that we actually use has got the phase added on. And all it has to discover is, have we reached the tick on point? If we have, we actually put the pin to 0. Have we reached the tick off point? And we put the pin to 1. Those have actually got flipped round, but I guess showing my mathematics. And that is all that does. There's one subtlety here, which is if we've had a change in frequency, then ticks off and ticks on will have changed. But I only ever let that happen when we do a tick on. So we don't change frequency sort of in the middle of an on period. It's just at the point we're about to flip from 1 to 0. If the frequency's changed, we update our local variable for that. The reason being is just to try to keep changes in frequency as clean as possible. So those are the oscillators. Okay, so the main loop. The main loop can run much more slowly. I wanted to keep this loop very, very efficient. So clearly with a 125 megahertz clock, we could have a square wave of half that, on and off with every clock cycle. But it's never going to reach that because it's got to do all this maths. I actually have a delay time of 10 microseconds, so it takes about 10 microseconds to get around that code. This is the main chunk of the code, and this does all the good things before we get going, like setting the direction of all the pins and getting all the whole GPIO going. This is for the standard I/O libraries which you're not actually using. I could probably lose this now, actually. I don't really need it. I always tend to sleep after initializing all the GPIO pins because they do slow stuff down. I'm going to edit that and get rid of the standard I/O because I don't need it. So here I'm setting up a value for tick on and tick off and the phase, setting them all to 0 and giving them a value. I think the center frequency starts at 140. Here we launch off the actual oscillators, and now we loop forever. This has got a 30 microsecond loop, but I imagine that talking to the analog to digital converter and all that stuff actually takes quite a long time. This ADC select selects the analog to digital pins. Cent is the center of frequency. Yeah, the analog to digital converter is quite noisy, so by averaging these out a bit, the center frequency and then the factor by which we spread, by averaging them out, it cuts the noise down. Because as the frequency moves, it does tend to make a little bit of noise on the output. Then we check for the button. If you press the button, we need to do a bit of maths, because when you press the button, it starts charging up, charges up. Because the longer you press it, the longer will be the release time. When you press the button, we want to start the attack phase, and in the attack phase, the volume ramps up. We set A to a very, very small number, but there's something else going on as well. There's this DEC variable, and what that means is the longer you hold the key down, the larger the smaller this value of DEC is going to become. DEC is going to be the rate at which we lose, or in the release phase, how slowly we kind of lose volume. What this means is that the longer you hold the key down, the longer it's going to take to fade away. And the value of decrements. If you in attack mode, then release is 1. The reason I've done this is that if you can press the key again to re-trigger. Attack value here, if you're in attack mode, then the value of A is ramping up. And when A reaches 1, then you've finished attacking. And if you're not pressing it, then attack 0, so the attack phase is over. Down the bottom here, if you're not attacking, then A is actually just, the amplitude is going to start being decreased linearly. So we've got an exponential up and then a linear down for the decay. And as I said, the longer you hold the button, the smaller the value of decay becomes, so the longer the decay will be. So that deals with the envelope. It's a very simple envelope. Press the button, the longer you press it, the longer the decay. The attack is quite short, so if you have a long attack, it uses this strange sort of... So the last thing to talk about here is the frequencies. This bit of code here takes quite a bit of CPU time, because we have to calculate the ticks on and ticks off value. So rather than the oscillator doing that, which is going to slow it down, or cause it to have a longer cycle time, we calculate the tick on and tick off here. The center frequency is the frequency that we've calculated from the knob up here. And then we take the square of the factor, and the factor is which oscillator we are. So the oscillators are laid out, their value is 0 to 16. So if we take away 7, take that away from 7, we get a negative number. So some of the oscillators go at a lower frequency and some go to a higher frequency. And I've also done it by the square of the difference. And that kind of gives us that the frequencies kind of spread out, and that's what that middle knob does. It kind of spreads the frequencies out. So there's the frequency, and then from the frequency we can calculate the ticks on, ticks off time. And the final thing we need to calculate is the phase. And the phase tells us, for the second oscillator, how far we're going to be out, which is related to the amplitude here. So when the amplitude is 0, the phase is 1 whole ticks on, which means they're completely out of phase. And that's the code. So thank you very much for watching. That is the hardware and software of the Microdrone covered. I'm wondering what to do with it now, whether to... Well, I've got to put the bottom back on, because it hasn't got a bottom. I'm wondering whether to give it away to someone. I'm wondering whether to build another one. Or should I just keep it on my desk? Because it's fun to just do that every now and then. I don't know. I'd appreciate any comments below. You know, what should I do with it? And if you want to build one, I've linked my GitHub below with the circuit diagram, and here you have the description. I really appreciate you watching, and I'm looking forward to seeing you next time on the Inner Loop. Just a little epilogue here. There's something I've missed with this Microdrone, and something I think I'm going to need to fix. My ethos for building this was, it's a quick idea, I'll build it, I'll put it in a box, and it's done. I'm not going to spend much time developing it or thinking about it. But having thought about it, and maybe some of you will already have said this in the comments, I realised that I'm only using 8 of the oscillators. I'm using all 16, but each pair remains locked in frequency. And there's some really interesting things I'd like to try, which is, what if you have 16 oscillators all with a random frequency, and you press the button and they go, and they all change, hop about. You press a button and then, with 16 different oscillators in just randomly chosen frequencies, that could be really interesting. And also, with 16 oscillators all spreading out in frequency, it could sound even more kind of rich. But that kind of implies that I need another button. I need a mode button. So in one mode, it runs how it is for this video, and then you press the button and it swaps to another mode, let's say the random mode, or the 16 oscillator spread mode, or some other thing. Or maybe you press the button and it changes the envelope type, like a very long attack and a short delay. So I think it might need another button, which really takes it away from the original idea, which is, that's the design, that's done. I might do that, but if you want to build one, you've still got the original code, you've got the circuit diagram, but I think I don't know, I think I might break my own rules and add another button and write some more code for this, because I really do feel that listening to 16 oscillators has got to happen.